A warm and professional greeting to you all. On the behalf of Kamaraj College of Engineering and Technology, Department of Electrical and Electronics Engineering, I am honored to welcome you all to the final day of our faculty development program on navigating the green revolution, integrating electrical vehicles and hydrogen fuel technologies for sustainable mobility. I would like to begin by extending a warm welcome to our guest speakers, facilitators, and participants. A warm welcome to our eminent resource person, Dr. G.R. Rajesh Khanna is an accomplished researcher and academician who gives a consent to share his expertise with us in this program. We are truly honored to have you with us and look forward to and praise this today's session. Over the past days, we have shared knowledge, gained new insights, and explored ways to enhance our teaching and professional growth. As we conclude this enriching journey today, let us carry forward the learning and collaboration that will help us shape a bright future in academia. The outcome of the faculty development program is to impart the knowledge on how to reduce the emission and improve the air quality through adoption of e-vehicles and hydrogen fuel cell technologies. It enriches us with broad outlines about infrastructures of adapting efficient and adorable transportation. It helps to enhance teaching, research, and professional skills of educators, equipping them with modern pedagogical techniques, technological advancements, and innovative strategies to improve students' learning outcomes. Before let's begin this session, I'm happy to introduce our today's resource person to this session, Dr. G.R. Rajesh Khanna, who is currently working as Deputy Research Associate at the High Energy Batteries Limited. Dr. G.R. Rajesh Khanna has completed PhD from Anna University, Chennai in the year of 2021. Completed his master from Anna University in the year 2015. He has completed his BE degree in the stream of Electrical and Electronics Engineering in Raja College of Engineering and Technology in the year of 2012. Dr. Rajesh Khanna has over 10 years of experience in academia, research, and industry specialization in power electronics, renewable energy, and CAD design. He had held a position of Deputy Research Associate at High Energy Batteries Limited and postdoctoral fellow at Kalasalingam University and research associate at Anna University and center manager and MEP design engineer and CAD engineer at Practical Technologies authorized by Mathur in Mathur. Power electronics, solar photovoltaics, hybrid energy systems, and energy storage solutions, BLDC motor devices, inverter circuits, and power system stabilities. He is certified professor for Autodesk AutoCAD, Autodesk Revit MEP, Fusion 360, MATLAB Simulink, PSIM, PLECS. He is master in design and development of embedded system and machine learning application using Arduino, STM32, PIC, and Atmel microcontroller. He has delivered lectures in various workshops and handles Omni training programs on AutoCAD, Fusion 360, electrical engineer, and power electronics at various institutions. Dr. Rajesh Khanna has published multiple international journal articles and conference papers in IEEE, Springer, Elsevier, and Taylor and Francis journals. In addition to that, Rajesh Khanna has published patents in the field of electric vehicle motor control and renewable energy system. He is the life member at India ISTE and senior member at IRED and a life member at IAENG and IEN. His contribution towards electrical vehicles, energy storage, and CAD training have earned him recognizing in both academia and industry. He continues to drive innovation in sustainable energy solution and electric mobility. With this note, I once again welcome our resource person, Dr. Rajesh Khanna, to address the gathering on the topic Advanced Battery Technologies.
Good afternoon to all. Thank you very much for your introduction about me, and I'm very happy to share my knowledge in the battery technologies, and I would like to thank Kamaraj Engineering College management for this opportunity given to me. Today I'm going to give the talk in advanced battery technology. I'm Dr. Rajesh Khanna, working as a Deputy Research Associate in High Energy Batteries, Mathur, Trichy. It is located near Trichy Airport, and I'm working in the R&D, Research and Development section. We are the pioneer in silver zinc battery, nickel cadmium, and then flow batteries. We are mainly supplying batteries for defense application, Indian Navy, Indian Army, DRDO, ISRO, and then NPOL, and many other government organizations. We are manufacturing the battery from lower ampere hour, that is millivolt cell, that is mainly used in launch vehicles and then space applications, to kilowatt level batteries. We are manufacturing nearly 330 kilowatt battery for underwater propulsion application, and then torpedo batteries, that is primary battery, which is also called as one shot battery, which is used only once. Once you have activated the battery, it will give full power, and it will be, the life of the battery will be over. The next one. Okay. These are some of our products. We are mainly concentrated in the chemistry of silver zinc, that we manufacture in both primary and the secondary battery. That is, we are manufacturing from 0.5 kilowatt to 330 kilowatt. Why our defense are mainly purchasing silver zinc battery means the silver zinc battery has more energy density. When we purchasing battery, we have to see two things. One is power density, another one is energy density. For domestic application, we are mainly purchasing the lead acid battery. In the lead acid battery, there are many limitations. For example, you have purchased any range of lead acid battery, the voltage range will be only 12 volt, but the ampere hour will be vary. So how first we have to look in how the power density and the energy density are considered in the battery. For example, if you want to increase the power range, means for example, if you want 24 volt battery, means if you increases number of electrodes in positive and negative electrodes in the battery, means the power density will be increases. If you want to increase the energy density, for example, if you run 500 watts load in the battery, means it is running for 2 hours. If you want the battery, you want to run in a 4 hours, means you have to increase the electrolyte that is stored inside the battery. By increasing the energy density, the charging and both the charging and the discharge time will get vary. That means it will increases. Our defense, in the Indian defense, they are mainly purchasing silver zinc battery for aircraft engine starting, satellite launch vehicle, aerospace telemetry, and then underwater propulsion. They are mainly buying this battery, silver zinc battery, for starting of the motor, which means it has more energy density. Within a fraction of a second, you have draw more power from this type of battery. But the silver zinc battery is very costly. The electrolyte in the silver zinc battery is KOH, that is potassium hydroxide. And we are also manufacturing and delivering the nickel cadmium battery. The nickel cadmium battery is used in aircraft engine starting, helicopter, UPS backup, and then army battle tank. I want to say a few advantages about the nickel cadmium battery. In the nickel cadmium battery, for example, any type of chemistry in battery, for example, lead acid, silver zinc, any other battery you purchase and keep it as ideal for more than 1 year, means the self discharge and the self life of the battery will be get reduced. But the nickel cadmium battery has more advantages. For example, if you simply purchasing the battery, for example, you purchase 10 number of battery, you continuously using 6 numbers and the 4 is kept ideal in the in your place. After 4 years, you simply change the electrolyte. That means you simply remove and then top of the kWh electrolyte in the battery, and then you do full, for example, 4 or 5 cycle, that is 4 times charge and 4 times full discharge, means the battery will come to the new battery condition. That is the main advantage of the nickel cadmium battery. The nickel cadmium batteries are nowadays mainly using in metro trains. For example, it is used mainly the Kolkata metro is using the nickel cadmium battery, because there are number of tunnels in the Kolkata. If the due to power shutdown, if the metro train stop inside the tunnel, means the nickel cadmium battery is used to take the train from tunnel to normal land area. That is the main advantage of the nickel cadmium battery. And in Asia, we are the only company we manufacturing the seawater activated battery. That is, we are working in 2 chemistry. One is silver magnesium and then copper chloride magnesium battery. It is the main application of this seawater activated battery is shown by flame, float, smoke, and then underwater propulsion. I will detail explain this seawater activated battery. So next slide. Next. Okay. This is the aircraft and helicopter batteries. This is this chemistry also nickel cadmium. You see there are ports at the end of the battery, which is used. The ports are the nothing but the battery terminals. For example, in the defense helicopter, there is a handle at the top of the battery. This shape of the battery is made according to the type of helicopters. It is easily fitted to the battery place that is provided in the helicopter. In the some other battery, there are extra terminals to be provided at the top. It will use to take the extra tapings from the battery. And I want to say what are the test condition we have to pass to deliver the battery for the defense application. In the land type version battery, there are a number of tests we have to carry out and we have to pass is very less. In the air applications, there are more number of tests we have to pass for get approved for the single model battery. For example, in the silver zinc battery we manufacturing 45 Ah, means we have to get separate. We have to pass separate test for that model battery. In the same chemistry, if you want to deliver the battery for 50 or 55 Ah, means we have to undergo separate test for that. For example, we manufacturing the battery and we do lot of tests in our company and delivering to the customer. After manufacturing of the battery, we going to supply the battery for the Delhi customer, means the battery will going to transport through the road condition. So from the road bump test, we have to do each and every test. For first test is road bump test and then vibration shock test. If the battery is going to use in the tanker, means the real vibration and the shock will be given to the battery and we will see the withstand condition. And charging and discharge test, we will go for deep discharge and deep charge for the battery. And again another one is chamfer test, which is used for climatic condition. If used to if the battery is going to operate in the deep cold condition, means we have to operate the battery at -40° or some other minus degree. If extreme hot condition, means we have the chamfer, which is we can test from -40 to +170° in the climatic condition. We all, so next one. And this is the underwater battery. I already told. In this battery, the battery is in dry condition only. It has positive and the negative electrode. There is no electrolyte is inside the battery. It is in dry condition. This type of battery, the cylindrical type batteries are mainly used to activate the torpedo in the submarine, or torpedo from the submarine. During the war condition, the torpedo will be activated from the submarine. The battery is attached to the torpedo. This battery is used to transfer the torpedo from submarine to the target vehicle. That is the main application. In this type of battery, there is no electrolyte is ready-made presented in this battery. The positive and negative electrodes are there in the battery. There is a cylindrical hole inside the battery. When the valve is open, the electrolyte is nothing but simply the seawater is the electrolyte. During the wartime, the valve will open from the submarine. The seawater will be flow to the battery. Then the battery will get activated and it will be travel with the torpedo, and it will be reaches the target. We are supplying this type of battery for up to 330 kilowatt, and we are also supplying both primary and the secondary version of the battery. This type also mainly silver zinc battery. I will explain what is the difference between primary and the secondary battery in the underwater activated battery. First thing, our Indian Navy purchasing the secondary type underwater battery for testing and trial purpose. Each and every day, the torpedo at the head of the torpedo, there will be a explosive fitted during the wartime. At the normal trial time, the dummy weight will be attached to the head of the torpedo, and then the in the secondary, for trial purpose, they use only secondary battery. In the secondary battery, we will not get full energy density that will compare to the primary battery. That is only used for the trial purpose. During the trial purpose, they simply activated the torpedo, and it will be, they fix some target, and the torpedo will reach us the target. After that, they take the battery to the submarine. They are, and again they put the charge and they repeat the trial again and again. But during the wartime, it is not possible, and we need more energy density of the battery to activate the torpedo during the wartime to reach the target. So they use the primary battery. In the primary battery, it is also in our language, it is also called as fire and forget. Once you activated the battery, means it will give the full energy and power, and the battery, the life will be closed. That is the working of the primary battery. In this battery, we will give the seawater and it will get activated. It will give full 330 kilowatt of power for only 15 minutes, and then it reaches the target, and the life of the battery will be over. And we are the only people in Asia we having test setup for this type of underwater activated battery. We will able to test up to 330 kilowatt of underwater battery. We having the simulated model for this one. During the testing, we place the battery at the open ground, and then we having the setup which is we created the artificial pressure for the electrolyte, which is going to operate in the seawater condition. For example, if the battery is going to operate in 100 bar pressure, means we artificially created the pressure, and we give the electrolyte to the battery at the same pressure, and we discharge the battery, and we give the report to the Indian Navy. The setup is only company we having in the Asia. In the seawater activated battery, for example, the small size battery has the weight of the small size battery is 3 ton. In this, I already told the chemistry of this battery is silver zinc. The weight of the silver will be nearly 1 ton. The 1/3 of the battery weight is full of silver. Okay, next. This is the one main battery, which is the chemistry of this battery also silver zinc. This is the onboard battery. I have already explained about the helicopter battery, and then seawater activated battery, lower ampere hour battery. This is the onboard battery, which is used in BrahMos. This type of battery is used to give the signal, and it will give power to all the display that is inside the BrahMos vehicle. this battery type standard is for the following version: land version missile, air version missile, navy version. This is only indigenous battery fitted used in the BrahMos missile. The another thing I want to say is in the silver zinc, any other chemistry, for example, the silver zinc battery, the battery case is made up of some fiber material. All other any other parts that we used in the silver zinc battery or nickel cadmium battery is indigenously made by us only. That is the main advantage of our company. This is the onboard battery. This we have supplied n number of batteries to for the BrahMos vehicle. This is the onboard battery. I have explained this one. In this, the electrolyte is KOS, that is potassium hydroxide. Once you give the KOH to the, you pass to the electron means it will get activated. So this is our patented work. I will explain this. The electrolyte is kept in the electrolyte tank separately. In between the electrolyte and the electrode part, there will be a plunger mechanism is placed. Once you want to activate this battery, means you simply attach to the on board, and then the separate lower ampere our battery is used to puncture the plunger mechanism. Once you give the supply to this, the diaphragm in between the electrolyte and the electrode will get puncture, and the electrode flow to the electrolyte will flow to the electrode, and the battery get activated, and it will give signal to the board. This is the main advantage of the battery. There are in this battery we differently use the plunger mechanism, so there is none other battery like this with this design is available in our country. Next one. This is the aircraft battery. The first one is the MiG variant. It is used for MiG aircraft. The bottom one is helicopter battery, which is used in our defense. We used this is a rechargeable battery, and the attachment and detachment is very easy for this battery. The top one is nickel cadmium battery. In this we have 12 cells which is connected in series and parallel to get the desired power for the particular applications. Next one. Next. This is our latest technology. Previous. Next. 7th slide. 8. Yes, this one. This is our latest technology. We working in this only. Now I am going to detail explain about the vanadium redox flow battery. Now vanadium redox flow battery, we have manufactured 0.5 kilowatt in the R&D stage. We have manufactured 0.5 kilowatt and 1 kilowatt, and then 5 kilowatt per 10 kilowatt hour, and then now we working in 10 kilowatt, 10 kilowatt, 50 kilowatt hour. That is the current work going in our company. Now we have already manufactured the 5 kilowatt VRB battery, and it is operating as standalone. It no need any person to operate. It is simply connected to the renewable energy, and now we're going to install this type of battery in the remote area, that is in the hill area, which is used to we're going to replace the diesel generator with this VRB battery in the remote area for the tower applications. I will explain detail about this one. We get the power from solar energy for the charging during the daytime, and the power from solar is given to two things. One is electrolyzer. Electrolyzer is used to generate the hydrogen, and the power from the hydrogen that generated from the electrolyzer is given as an input to the fuel cell. The fuel cell need hydrogen and then air or oxygen. if we're going to operate the fuel cell in oxygen, means the amount of hydrogen and the oxygen level will be equal. If we're going to operate the fuel cell in hydrogen and air, means the amount of air required to operate the fuel cell is 5 times higher than the hydrogen. That is the difference for hydrogen oxygen fuel cell and then hydrogen air fuel cell. The power from solar energy is given as an input to the electrolyzer. By consuming this power, the electrolyzer will generate the hydrogen. The generator hydrogen is compressed to particular pressure and then it is given as an input to the fuel cell. Also, the power from solar energy is given to charge the VRFB battery, that is vanadium redox flow battery. The flow nowadays the flow battery is growing very fast. It has many advantages when compared to the other traditional batteries. Now we also working in 20 kilowatt per 100 kilowatt hour, that is containerized solution, which is in a single container, the battery, the electrolyte tank, all the power electronics control system, all are kept in a single container. We are working in that only. The next one. This is the electrolyzer we having the setup in our company. It typically 3 kilowatt electrolyzer. That is the main advantage. There are many type of electrolyzer. That is alkaline, proton exchange membrane electrolyzer, anion exchange membrane electrolyzer. In this type, the operating temperature will be very high. See, the alkaline electrolyzer will be operated from 65 degree to 100 degrees Celsius. The proton exchange membrane electrolyzer will operate 50 to 90 degrees Celsius. The anion exchange membrane operated 50 to 80 degrees Celsius. And this is the voltage level for the each cell. Nowadays we are working in the membraneless electrolyzer to reduce the cost, and for more efficiency we are working in the membraneless electrolyzer, and we having 3 kilowatt plant. In a single day we will produce 12,600 liter hydrogen, and we working in compressed and then storage unit of the hydrogen. Next. The another one is fuel cell. You all hear about the fuel cell. The fuel cell, the input for the fuel cell, this is different from the normal battery. We all know that the battery is a storage device, but the fuel cell is the energy. Battery is the energy storage device, but the fuel cell is the energy conversion device. The fuel cell is used to convert hydrogen and oxygen energy into electrical energy. The main advantage of the fuel cell is we no need to wait for charging time. You simply fit the hydrogen and the oxygen cylinder, or if the fuel cell is the open cathode system, means you no need oxygen also. You simply fit the hydrogen cylinder. The cathode side fuel is the air that it will be get from the atmosphere, and we supply air to the cathode side by using the blower, and we get the power immediately. That is the main advantage of the fuel cell. We working in PEMFC, that is photon exchange membrane fuel cell. We have already manufactured 1 kilowatt. Earlier we have supplied n number of fuel cells, phosphoric acid fuel cell to the DRDO. That is 500 watts fuel cell. Now we are working in 1 kilowatt PEMFC fuel cell. And there are a lot of challenges in this type for the high power fuel cell. That is mainly thermal management and then leak proof. There are a lot of challenges. We are working that only. The main advantage of fuel cell is high energy density, and each and every cell efficiency is 50 to 70%. This is the main problem in the fuel cell. The operating temperature is 60 to 120 degrees Celsius. Once you scale up, means the temperature of the fuel cell will get increases. The fuel cell will be operated at the good condition only when the cell reaches the 60. Once you ready to load the fuel cell, mean the temperature will be rise fastly. That is the main disadvantages. And this is a zero pollution environment. The fuel cell is a zero pollution environment. Nowadays many of the electric vehicle companies moving from lithium ion battery to the fuel cell. We are also working in the lithium ion, but we are not manufacturing the lithium ion cell. We are mainly working in second life lithium ion. That means we purchasing the lithium ion pack, that is used pack, which is worked in automotive applications. We purchasing the pack and then we dismantle everything. We have cycler. In that cycler, we will test the lithium ion, any type of cylindrical, whatever chemistry may be. For example, lithium pyrophosphate or NMC or titanate, anything which it is in cylindrical form means we will cycle the battery 256 battery at a time. After that, we will filter all the battery. For example, if you're purchasing the used lithium ion battery from that is used in automotive application means if I test the 100 cell means nearly 95 to 96 cell will has the 80%, more than 80% of efficiency, which is ready to work for static applications. And after this test, we will do IR test. We have IR tester. We will filter 10 ranges, and then we select the battery for each pack, and we made that each cell to the battery pack, lithium ion pack. After making that pack, we have cell pack tester. We will test up to 400 volt battery pack. After doing that, we will use it for our application. For example, we for social project, we install near 100 number of solar street light to the nearby people working in our second life lithium ion battery. In our inside our campus also, we having many number of solar lights working in our lithium second life lithium battery, which is operating working in the same condition for more than 2 years. Next one. This is the energy storage. This is a global cumulative energy storage installation in 2024. The lower pie chart, the below left side pie chart showing that the what are the energy resources that are available. The most one is electrochemical, another one is non-electrochemical. See, more than 50% the energy storage depend on the electrochemical side. The second one show that what type of electrochemical is they want. Lithium nowadays they are mostly using the lithium ion battery. The lithium ion battery is going to replace by hydrogen based batteries and then flow batteries. Next one. This is the main thing. Why do we discuss about the energy storage? The graph is plotted between the specific energy and the specific power. For example, the capacitor has more specific power, but the specific energy is less. But when come to the batteries and fuel, the main disadvantage of the fuel cell is it has more specific energy, but the specific power is less. If we go for more specific power, the thermal management and then cooling system, the size of the fuel cell will be more. That is the main reason. But when come to the normal flow battery or normal battery, the energy, specific energy and the specific power is moderate. Next one. Okay, now we come to the topic why we are speaking about flow batteries. The flow battery is long duration energy storage in key to unlock the full potential of the renewable. No single technology can meet all demands. There are lot of flow batteries. We are working in vanadium redox flow battery. That is the most benefited battery. There are zinc bromine battery, but the zinc bromine is not environmental user friendly. So we're working in vanadium redox flow battery. I explain detail about the vanadium redox flow battery. The market require reliable, low cost, safe battery storage for both high power and the high energy application. That is the main benefit. In the VRFB, we will go for high power and then both high power and the high energy. The lithium and lead acid are good for short duration storage, but it is not used for full day energy storage application, the lithium ion or lead acid are not possible. The super capacitor are good for high power for few seconds only. And the lead acid flow battery are suitable for large scale energy storage up to megawatt level, and then long backup time. For example, up to a day we will use the vanadium lead acid flow battery. Next one. A redox flow battery is an electrochemical storage technology where energy is provided by two chemical components dissolved in a solvent that are pumped through the cell on separate side of the membrane. I will simply explain the construction of the battery. For easy understanding, I will compare this battery with the lead acid battery. In the lead acid battery, I have already told that the power part is the electrode, that is positive electrode and the negative electrode. If we using the battery for UPS means there is six cells inside the lead acid battery. Each cell has 2 volt and it is connected in series. The total capacity of the battery is 12 volt. For example, if you purchase low ampere hour battery means the size of the battery is flat and then it will low. If you buy high ampere hour battery means the size of the battery is more, because we want to store the electrolyte in the battery. During the charge condition, the electrolyte will get charged. During the discharge condition, electrolyte discharge and we consume the power. That is the simple concept of the battery. Now I compare this battery with the vanadium lead acid flow battery. Like the same only, we will have the another thing I want to say is we mainly working in, for example, I will explain about the silver zinc battery, nickel cadmium, copper chloride battery. In all those battery, we are very much expertise in low voltage high ampere hour battery. For example, I say one power rating of the nickel cadmium battery in our company that we manufacturing for tanker application. That is, the voltage range of the battery is 1 volt, but the current is energy of the battery is energy density of the battery is 1000 ampere hour. With 1 volt battery, we will able to consume 1000 amps in a single shot. That is the main advantage of our company. In the vanadium lead acid flow battery, so go to next slide. I will explain. There is a schematic diagram. The main global player for the vanadium lead acid flow battery is Ronke Power. They are manufacturing up to 400 megawatt hour. Sumitomo Electric Industry, they manufacture up to 51 megawatt hour. Infinity, they install 22 megawatt hour. Cellcube 8 megawatt hour. In the India, high energy battery manufacturing the VRB battery, and Electric Delhi is manufacturing, VFlow Tech manufacturing the battery. When compared to the lead acid battery, in the vanadium lead acid flow battery, the energy part and the power part will be separate. So there is no problem. See, there is 2 tank that is in slow in this slide. A cathode tank and the anode tank. Each amount of electrolyte is taken in the both tank. That is vanadium. The state of the solution is V4. During the charging time, reduction will happen in the cathode side and the oxidation will happen in the anode side. During oxidation, the V4 ions will be transferred into V3. During reduction, the V4 ions will be transferred to V5. This vice versa will be happen during the discharge condition. So again and again, the electrolyte will be comes to the initial position after charge and discharge. That is the main advantages. This will be a long-term energy storage in the combination with renewable energy sources. Power and energy rating is decoupled using a variable stack and electrolyte volume. The right side image is this type of setup we are having in our company, that is 5 kilowatt but 10 kilowatt hour VRB battery, which is demonstrated in the Goa during last year India Energy Week. The bottom section has the 2 tank, which is anode tank and the cathode tank. The top section is the battery, which is the power part. I have already told. For example, the reduction flow battery is suitable for long scale energy storage, kilowatt hour to the megawatt hour, and then long backup time up to a day. VRB can perform more than 10,000 cycle over 20 years. Aqueous based system, environmental friendly. Sir? 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 Previously, sir, previously. Yes. In the below right side image, the top one is the power part. The 5 kilowatt stack consists of the 44 cells. For example, I have manufactured the 5 kilowatt cell. Again, one customer is asking, I want not I want 5 kilowatt, I want 7.5 kilowatt cell. Means I have simply dismantle the end plate at one side, and I will introduce another 22 electrode. Means the power part will converted from 5 kilowatt to 7.5 kilowatt. Another customer, he asking 5 kilowatt hour is okay for me, but I want more energy density. I want to run this amount of power for 15 hours. Means I simply added catholyte and anolyte, that is chemical, vanadium chemical to the anolyte and the catholyte tank. Means the energy density will be increased. That is the main advantage. There is no restriction in the power and energy part in the VRFB, and it is very environmental friendly because it will operate only at 32 to 40 Celsius. So there is no appropriate increases in the temperature. The only thing we have to do is we have to for equal interval of time. For example, within a 6 months once or a yearly once, I got to check the state of chemical, and then I will add some salt. Means it, vanadium salt means the electrolyte will come to the normal stage, and I have operated. Hello. Hello, sir. The next one. Next one. Hello. Next. 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 This is the chemical reaction that. Okay. Stop. Okay. The left hand shows the exploded view of the single cell assembly. At the end of the VRB battery, end plate is attached, which is made up of aluminum, which is used to hold all the cells together, and then the current collector is placed, which is made up of pure copper, 99.9% copper. If we want more efficiency, means we will simply coat the copper with the pure silver. And next one is the electrode. The electrode we have optimized many things. I will show in the next slide. In the electrode we have optimized the flow pattern, and then the electrolyte we have optimized what is the optimal and what is the flow rate for the battery, and then how much amount of electrolyte that we pump for the equal interval of time. By our experience, we have simply by seeing the solution, we will easily identify the state of that vanadium solution, that is anolyte or catholyte. If the vanadium is in 2+ oxidation state, means the color of the solution will be violet. If it is 3+ solution, means the color of the solution is green. 4+ means blue, and 5+ means the color of the solution will be yellow. Next one. This is this small setup, which is 4 cell assembly, that is 150 centimeter square cell, which is used for demonstration purpose and for validation for various flow pattern and then electrolyte. Next one. This is our main work that will carried out inside the flow pattern. I have already told that the anolyte and the catholyte will be going to flow at the two side of the electrode. The that is the bipolar plate. At the both sides it has the flow pattern. The first one is the parallel flow pattern. Second one interdigital flow pattern. Interdigital means for particular interval there will be some interdigital flow. The third one is pocketed flow pattern, which means there is no flow pattern. It is a flat electrode. There is no flow pattern. The fourth one is the serpentine flow pattern. Next slide. Using the COMSOL software, we will calculate the pressure drop inside the electrode for the different flow pattern. Next one. This is the strength of the flow pattern. The thickness and the width of the electrode and the depth of the flow we have designed to increase the strength while the electrolyte will be flow to the flow battery. Again, another one thing I have to say is the power part and the energy part is connected with the pump. There are two pumps which is connected to the catholyte and the anolyte. And during charge, both the charging and discharge time, the electrolyte has to flow inside the battery. So the pump will be operated. Both two pump will be operated both during the charging and the discharge time. Next one. I have already said that we have optimized pressure drop on the flow rate for the battery. For example, how we going to decide the amount of flow that will be go to the battery means in the flow I am talking about the flow in the vanadium redox flow battery. 1 ml of solution for 1 centimeter square for 1 minute. That is the calculation. I am again telling 1 ml of solution that has to flow inside the battery for 1 centimeter square area for 1 minute for 60 seconds. That is the calculation for flow of battery for the this is the flow that we have optimized for higher efficiency. The first graph shows the comparison of pressure drop between different flow patterns. See, the pressure drop is high if the flow pattern is serpentine. The pressure drop is low for the below one is convergent divergent flow. The pressure drop is moderate compared to the flow rate in the interdigital flow pattern. The second figure shows that the pressure drop measured using the inverted U-tube manometer. This setup is we made to calculate the pressure drop in the VRB cell. Here we calculated by using the single cell assembly, and then we calculated for the full stack. Next one. This is the GCD performance, which is plotted between the voltage and the capacity ampere hour for each flow pattern. The first one is plotted for serpentine flow pattern and the convergent divergent flow pattern. First one, and the second one shows the capacity and the voltage level, which is for 5 ampere and 10 amps and 12.5 amps and 15 amps. Next slide. This is plotted between the EA study and the IV characterization. The Nyquist plot of VRB cell performed by circulating both anode and cathode by external peristaltic pump at the open circuit condition at the end of the first discharge. I will explain. By before during doing this test, at the initial stage we have charge the VRB battery to the full charge condition, and then we discharge for the full, and then after the first cycle only we will do this test during the at the open circuit conditions. The galvanostatic polarization of the VRB battery at the different current density we have plotted. For example, we have plotted for serpentine flow and the convergent divergent flow pattern. Next one. The key parameters in the VRB design and development. The battery engineering are crucial in the industry for developing, improving, and implementing battery technologies. At the initial stage, we have faced lot of challenges in designing and implementing the VRB battery. Now we have optimized many things and we come to some conclusion. Now we ready to supply the commercial stage of the battery. First one, the above part, that is the stack and the power part, that is positive and the negative electrode. And I also explain how it's work means. I already told there are 4 openings in the power part in the VRB battery, that is anode in and anode out and cathode in and cathode out. It will flow to the bifacial plate, which is simply the graphite plate, and machined at the 2N with the different flow pattern, and it is separated by the above each plate, and at the end of each plate we will keep the carbon felt, which is look like a glass wool, which is during the flow the carbon felt will get soaked and the conduction will be take place there. To separate the anode and the cathode electrode, we will place the membrane. There only ionic exchange will be take place in the ionic exchange will take place in the membrane only. Now we are purchasing the commercial membrane and we are working for the in-house membrane. We working for that only. For example, if we purchase the VRB battery, for example, the cost of the VRB battery is 1 crore means, for example, the 10 kilowatt battery is 1 crore means the cost of the membrane is 40% of the battery cost. That is the main disadvantage. Now we are working for the in-house membrane. The second, electrolyte and the energy part, that is the chemistry part. Here we are going to analyze the electrolyte composition optimization, state of charge, state of health, OCV, and etc. The piping arrangement and the balance of plant. It is designed by the mechanical and the chemical engineering. We have considered P and ID, and then corrosion. What type of material we have to use to prevent corrosion, and the material that we selected will not degrade the chemical that we used in the battery. These are all the matter we have to consider during selection of piping arrangements. And the power electronics section, that is electrical and electronics engineer, that is mainly consists of charger, inverter, and then other control units that we used to couple the battery with the load side, and safety and stability. Okay, next. This is the 1 kilowatt 10 kilowatt hour VRB battery. This battery consists of the 24 cells. The area of each cell is 600 centimeter square. The current density per milliampere per centimeter square is current 100 milliampere per centimeter square. That is the current density that we consider in this 1 kilowatt bar 10 kilowatt hour VRB battery. The terminal voltage is 24 to 33. That is the terminal voltage, and the current passing through the cell is 60 amps. The battery round trip efficiency, that is 80 to 90%. We claiming this amount of efficiency after full 300 cycles. 300 time charge and 300 time discharge only, we come to conclusion that the battery will give 80 to 90% of efficiency. And the maximum depth of discharge is 85%. That is the main advantage of the VRB battery. In some other battery, if you do deep discharge means it is very difficult to bring the battery to the normal stage. The charging current, it need more charging current, and the charging time will increases, and the degradation will be happen in the battery. But there is no that kind of problem in this type of battery. For example, due to deep discharge, there is a degradation in the electrolyte means we will simply add some chemicals to the electrolyte, and it will be, we bring the electrolyte to the normal condition. That is the main advantage of the battery. And at any time you can increase the energy part or decrease the energy part, or increase the power or decrease the power part. That is the main advantages. And the main thing we have to consider is, by using the membrane only, the conduction will be take place inside the VRB battery. by selection of membrane, and we have to do proper treatment, membrane treatment. Due to that only crossover will be reduced in the battery. If the proper selection, the proper treatment will not happen in the membrane, means that crossover will be happen, and then for example, I'm saying the level of the analyte will be increases and the level of catalyte will be decreases in the tank. So the chemical changes will be take place on the life of the battery, and then uh, efficiency of the battery will get reduced. That is the main thing we have to consider during the design of VRF battery. Next. I have already told that this is the 5 kilowatt but 10 kilowatt hour. This is standalone battery, which does not need any electric supply from EB side. We using full solar for charging, and then we using this power for our electric vehicle. The employee who are having the electrical vehicle, we providing power from this VRB battery for the study purpose, and then they charging their vehicle by using this battery. Next one. Okay, this is the scale up design that we used in the 5 kilowatt hour. The first one is the left side first part is end plate, which is made up of aluminum. The second one is the insulation, that is a Teflon sheet. The third one is current collector, which is made up of 99% of pure copper, and at the surface of the copper plate we placed silver foil to get more conduction. And for the sealing purpose we will use rubber gasket next to the copper plate, copper current collector, and then end electrode. End electrode is nothing but a unipolar plate which has flat surface at one end and then flow pattern at the other end, and then again placed with the rubber gasket, and then we place membrane which is used to separate anode electrode and the cathode electrode, and again and again we will place the bipolar electrode, and at the end of the battery will place the unipolar plate, and then current collector, and then insulator, and then end plate. This is the arrangement of the VRFB 5 kilowatt per 10 kilowatt hour battery. Next one. This is the completed stack, and the common manifold is shown here for your easy understanding. The manifold is as 2N. It has four manifold, that is anolyte inlet, anolyte outlet, catholyte inlet, and catholyte outlet. Next. And this is the piping and plumbing arrangement. There are two pumps which is connected at the anolyte tank and the catholyte tank. It will pump the solution to the power part of the battery. The anolyte tank give the anolyte, the solution from anolyte tank is given to the anolyte input of the power part, and the catholyte chemical is pumped to the power part of the battery to the catholyte inlet. The outlet part will be again connected to the tank. The solution will be circulated during charge and then discharge condition. Next. This we now working. We have already designed the 5 kilowatt per 10 kilowatt hour. Now we working for standalone containerized system for 10 kilowatt per 50 kilowatt hour. For example, if the customer purchase the single container, they simply transport the single container and then place that where they want to place the container, and then simply take the power from the battery. This is what we nowadays working. We working with combined with the ONGC, IIT Madras, and then the HEB people are working in this project. Next. This is how VRB battery is connected with the solar. The solar photovoltaic, we all know this power is a powertrain system. The solar photovoltaic is connected with the PV panel, connected with the solar charger controller, and then The EB power also connected to the charger. During the night time, if you want to charge the battery, means the power will be consumed from the EB, and then the battery will get charged during the discharge time. By using the inverter, we will give on to the load. Next. This is the power trains that we used in the 5 kilowatt per 10 kilowatt hour. From the we get the power from both solar and the EB. During daytime, the battery will get charged by using the solar power. During the night time, the battery will get charged by using the power from EB. And then many control systems are used. For example, if I claiming 5 kilowatt, 5 kilowatt VRB means in the power part of our battery is 5 kilowatt means we want generator accurately 5 kilowatt. We will generate nearly 7.5 to 8 kilowatt. I already said that during both charging and discharging, the two pump is going to operate for circulating the electrolyte, that is anolyte and the catholyte. So full 5 kilowatt is given to the load, and remaining 1.5 or 2 kilowatt is used to run the pump during both charging and the discharge condition. Here, to maintain the pressure drop and then pressure distribution, the flow inside the battery, we are using the magnetic pump. Based on the pressure, the flow of the pump will be get tuned based on the pressure. So we are using the magnetic pump for this type of battery. Next. Next. EV charging station. For example, if you want to charge the vehicle in the road condition means you will wait for some time. For example, if you charging your vehicle in the home means you would simply put charger during the night time and you switch off the charger during the morning time. So the normal charging will be take place. So the life of battery will not get degraded. In the roadside, if you're going to charge means you mainly going for a fast charging. If you do fast charging means the life of the battery will going to reduce. So the battery swapping station is also there. It is very easiest method. You're simply going to stop the vehicle, you're swapping the battery, and then you start traveling. The main nowadays many swapping stations are charging the battery by using the VRB. They no need external power. They if they purchase containerized standalone VRB battery means the VRB battery is going to get charged by using the solar during the daytime, and the battery and the EV battery will charge by using the power from the VRB battery. That is the main advantage of the VRB battery. Next one. Next. This is the EV charging station control room. The blue color line shows the communication line. They used to transmit the signal, and the red color line shows the power line. Next. This is the small charging stations setup that we having inside our plant. We charging the VRB battery by using the solar, and then power from VRB battery is used for charging our in-house vehicles. Next one. Next. These are some of our previous one. These are some of our plant, our company plant. That is, first one is silver zinc battery facility. Here we manufacture lower ampere hour to 330 kilowatt battery, and the R&D laboratory. We having electrochemical workstations, chemical labs, mechanical lab, electrical lab. All R&D activities are happening here only. I will explain about the seawater battery facility. And last one is lead acid battery. Now there is no bulk manufacturing is happening there. Previously, we have manufactured valve regulated lead acid battery. In that battery, there is no openings, and the electrolyte is in the gel form. So there is no fumes that will generated during the charging and discharging. We are the before we are manufacturing of the VRLI battery. Now we are not manufacturing. The VRLI battery is mainly used in automotive applications and then UPS applications. And this one is mainly working nowadays. We are working in the seawater battery, which is I explained in detail. Now we are working this type of battery for NPOL, National Physical Geographical Limited. It is in Kerala. We testing the battery in our facility. The anode of the battery is magnesium alloy and the cathode of the battery is carbon dress. The battery is very similar to the sodium air battery. That is, the sodium air battery is mainly used in Africa countries. The people who are living in the remote area, they simply take the seawater in a bamboo and then they connected the low voltage bulb in that. By using the dissolved oxygen in the seawater, the bulb will be glow for few days. Like that similar application only we use we working in the seawater battery. I already said that the anode of the battery is magnesium alloy and the cathode is carbon dress. This type of battery we connect only in a parallel connection. We do not do serial connection in this type of battery. The NPO is going to place the battery in underwater below 1000 feet from the seawater level. It is a the name of the battery is long life seawater battery. It will be give power for long time, that is minimum 1 year. After that, there will be degradation due to the corrosion in the magnesium alloy due to seawater. The output of the battery is, I have already said that we are able to connect only this type of battery in parallel. We do not do the series connection. If we do series connection, mean there is no any changes will happen. So we connected this type of number of cells in a parallel connection. The output of the battery is 5 amps 1 volt, and by using the boost converter we are converting to 5 volt 1 amps, and this amount of power will be we get from the seawater battery for minimum 1 year. This is the upcoming project that is going in our company. Next. Next. Acknowledgement. Our group company SSI Paper and Board Limited, SPB PC, and then Ponni Sugars, SWIN Advanced Technologies. And our R&D collaborators are DRDO, ISRO, IIT Madras, ONGC, Center for Higher Technology, GAIL, New Trace, Amrita Vishwapidam, Kollam, Coimbatore, and then PSG College, and Cellcube, Yanajrak, GmbH. These are our group companies and then R&D collaborators. Okay, thank you. Any questions, please ask me.
Good afternoon, sir.
Good afternoon, sir.
Myself, Dr. Rajesh from NPR Engineering College.
Okay, sir.
So, if possible, we visit your company, sir, R&D cell.
Yes, sir. You visited fuel cell section, VRFB, lithium-ion second life, and then electrolyzer. You able to see all those facilities, sir.
Okay, okay. In which time, how to get this permission to your?
Sir, you simply send a mail to our HR, sir. It is available in our website.
Okay, okay, okay.
And you ask the convenient time from here.
Okay, sir. Okay.
And then you will visit our company, sir.
Okay, sir. Okay. Thank you.
Thank you.
Thank you for your nice presentation. Thank you, sir.
Thank you very much, sir.
Sir, good afternoon, sir.
Good afternoon, sir.
Hello. Myself, Dr. D.S. Naidu, sir, we're from Andhra.
Okay,
Sir,
sir.
we want to install some solar lights to our college, sir, actually converted into green campus. Can you
Okay,
give
sir.
some suggestions, sir, which battery or which lights, which one? Maybe it is available in India, sir, or you want to purchase that
Sir,
lights
for
from...
solar light, you better go for lithium ion, sir.
How much capacity, sir? Batteries, sir. Lithium ion is okay.
Yeah, at any voltage and any current level, we will give the pack, sir.
Okay.
You simply send the requirement for me, and I will send the code to you, sir.
Okay, sir. Thank you.
And if you interested, means you purchase a battery pack from us. We will customize a voltage and current level based on your application, sir.
Okay.
With
Because
BMS or
we
without
want to
BMS.
save 30% of energy. Based
Okay,
on
sir.
that, the campus will be converted into green campus, sir. Actually, we have an
Okay,
MSS
sir.
companies
Sir,
as well as college. Okay,
share
engineering.
tell your mail ID, sir.
My mail ID MEC HOD MEC, sir. MEC
HOD
HOD at the rate Miracle Educational
Miracle.
.com. Miracle, MIRACLE.
Education.
Miracle Educational Society.com, sir. I will share, sir, in the chat box.
Okay, sir. HOD MEC or MEC HOD, sir?
MEC HOD, sir.
MEC HOD, okay, sir. Okay. Any other question? Any other question?
I request the participant to interact with the resource person.
Sir.
Any other question, sir? Sir, can you wind up the session, sir?
Deeptika.
With the growing
Sir?
Okay, Rajesh.
Okay, sir.
Deepika, you can formally conclude.
With the growing demand for electrical vehicles, renewable energy storage, and portable electronics, advanced battery technologies are crucial for improving efficiency, lifespan, and sustainability. This session will explore the latest advancement in battery materials, designs, and applications. Advanced battery technologies are shaping the future of sustainable energy and electrification. This session highlights the how to enhance energy density, reduce cost, improve safety, and support green energy transition. And it provides participants with insights into cutting-edge developments and their real-world applications. We sincerely thank Dr. Rajesh Khanna for sharing his valuable insights with us during the faculty development program. Your expertise and knowledge have truly enriched our learning experience. We deeply appreciate your time, effort, and dedication. Looking forward to more such enlightening sessions with you. Thank you, sir.
Thank you very much.
I request all the faculty members to stay online for the next session, which will be started in 5 minutes.
Thank you very much, sir.
Thank you, Rajesh. Thank you.